Assalamualaikum warahmatullahi wabarakatuh. Today, in this video, we are from Group 5 here to present our digital logic project called Network Packet Transmission Monitoring System. So first and foremost, I want to introduce our group members. The first one is Ahmad Wildan bin Amazani. The second one is Mikael Hakimi bin Naha Junaidi. The third one is Muhammad Alif bin Helmi. And lastly, myself, Muhammad Fidaus bin Malani. So let's begin with the background. So the first one is to create a digital circuit that monitors the network packet transmission. The second one is to implement knowledge gained from this course by simulating a real case outside the classroom. And lastly is to design and simulate a circuit to execute the packet transmission using DITS simulator. So let's go on with the components that is used in the complete system. So for the connection from lab 1 to lab 2 or lab A to lab B, we used a multiplexer for lab A or lab 1 and also a demultiplexer for lab 2 or lab B. Next, we use a count up counter function. So in this function, we used a synchronous 4-bit counter as well as T flip-flops. Next up, we use comparator function. In this function, we used a 4-bit comparator only. Next, the clock enabler function. In this function, the AND gate is involved. Next is the monitoring packet transfer function. For this function, it is actually a combination of the previous functions. So, and also we use some additional components as well. The first one is the multiplexer. Next is the demultiplexer, basic logic gates, LED tester, output 4-bit LED array, single bit output, and also the hex display. Next is the display controller function, which is a fun concept. And for this function, we used a push button. Lastly, the clock enabler rules. So for this one, the clock enabler actually has 4 inputs and 2 of them are advanced, which we improvised ourselves. So for the improvisation, we used a 3-digit password and also a clear bar value.
Alright, now let's move to the problem part. Firstly, computers in lab A and lab B communicate via a single codes cable for data transmission. It is required a precise data handling, synchronization, and password security. On top of that, the challenges include inefficiencies in data transfer and flow management. Constant monitoring is needed to ensure accurate and error-free transmission. Moreover, disruptions also can cause delays, data loss, or system malfunctioning.
Now, we move on to the suggested solution. So as you can see displayed on your screen right now is the block diagram of our complete circuit. Firstly, the top left corner. This is lab A, in which 6 computers are connected to a source collector, i.e. a multiplexer. So as you can see, each computer consists of a power button and a data generator to simulate the generation of the data in which it will be transmitted. When the power button is switched to 1, which is high, and the data generator is turned on, the data from that computer will travel to the source selector. Next, we move on to lab B. So as you can see, lab B is located in the top right corner. So inside lab B, there is a destination selector, i.e. a demultiplexer. So connected between lab A and lab B is an AND gate. So, for example, I want to send data from lab A, computer 1, to computer 1 lab B. So if the power of computer 1 in lab A is turned on and the data generator is turned on as well, the data will travel from computer 1 lab A to the source selector, and the data will be selected and will travel from lab A to lab B. So for example, if I want to if I want the destination of the data to be at computer 1 as well, I will set the destination of the demultiplexer to computer 1, in which the data will go from the destination selector, i.e. the demultiplexer, and if the power button of computer 1 is turned on is 1 as well, the data will travel to computer 1, thus completing the data transmission process. Next, we move on to the clock enabler function. So the clock enabler is the system where it enables the data from lab A to be transmitted to lab B. Because as you can see, the AND gate that is located between lab A and lab B, one of the inputs is the clock enabler. So if the clock enabler's output is 0, the data from lab A could not be transmitted to lab B. So essentially, the clock enabler must also be 1 in order for the data to be transmitted. So what are the conditions for the clock enabler to give an output of 1? The first one, the password must be correct. The second one is the controller must be pushed. The third one is the clear bar switch must be set to 1. Next, at least a computer from lab A and lab B must be turned on. And lastly, the counter value must not be equal to the maximum packet of data to be transmitted. Moving on, we will look in detail regarding the password system. So the password is a 3-digit password where the digits are in the form of hexadecimals, which means that each digit has 16 possible combinations. When combined with the other two, we have a total of 4,096 total combinations. If an individual wants to break into the system, the chance of guessing the correct combination is 1 out of 4,096 or 0.024%. Now let's look into the counter function. So this counter is a count up counter in which it will increase by 1. So for this counter, we use 4 T flip-flops in order to build a 4-bit counter. So the counter is able to increment by 1 for every iteration of the button from the controller is pressed. The counter starts at 0 and it increases by 1 until it reaches the maximum packet of data that is predetermined by the user beforehand. Lastly, let me give you the details regarding the counter comparator. So the counter comparator is used to set the maximum packet of data that is going to be transmitted from lab A to lab B. It includes a comparator component to compare the amount of data sent and the maximum data that is able to be transmitted. Once the total amount of data is at the maximum, the counter that is connected to it will stop and no data will continue to be transmitted.
Now, let's move to the requirements part. First of all, we need input switch to power on selected computers from lab A and lab B to control clear bar input all flip-flops. Next, we need input hex digit to set maximum amounts of packet data for transmission and to enter a password. Input push button is to send a clock pulse to the counter. A clock generator acts as a data packet. Multiplexer, or we known as MUX, is to select source computer for data transmission. Demultiplexer, or we call it as a demux, to distribute the received data to the selected destination computer. Decoder is to determine truth value of password entered. Next, comparator. What is function of comparator? Comparator is to compare counter value with the maximum amount of packet data for transmission. Next, counter. To count the number of packet data that have been transmitted. 7-segment display is to display the current packet count being transmitted. Clock enabler Clock enabler is to control the clock signal to the counter, enable the counter when certain conditions are met. Sync data. Synchronized data flow between selected computers during transmission. Lastly, LED display is to provide visual feedback for successful data transmission. That's all from the requirements.
Let's jump into system implementation. So, system implementation of our project, which is designed to facilitate secure and synchronized data transmission between two labs. The system is built using logical components such as multiplexers, demultiplexers, synchronous counter, and clock enablers, ensuring efficient and controlled communication. To make it easier to follow, I will break the implementation down into several key components. So let's start with the source selection, which is Lab A. Lab A has 6 on switches, each used to power on a specific computer. To enable data transmission, the selected computer must be powered on by setting its corresponding switches to 1. Once the selected computer is powered on, its source address must be configured using the source switches. So, the sources switches are in binary format. Source 0 represent the least significant bit, LSB, and source 2 represent the most significant bit, which is known as MSB. For example, if we want to send data from computer A, we are going to set A to 1, which power it's on, and source address to 100, which it translates to computer A5. This ensures that the correct data source is selected before transmission begins. So, for destination selection, similarly, in Lab B, we have another 6 on switches used to power on the selected computer that accept data transmitted from Lab A. Once the selected computer is powered on, its destination address must be configured using the destination switches. Again, we assign a destination address using 3 destination switches, following the same binary logic as Lab A. For example, if computer B3 is the destination address is 010. By having this structure on switches and address, we ensure that data is sent from the correct source and received by the correct destination. So for Keybar, this switch is used to ensure the counter operates in synchronous mode by setting it to 1. So for the next one is system implementation input hex digit. So one of our essential input parameter in our system is packet data. The user must set the maximum number of bytes or packets to be transferred by configuring the packet data input to the desired packet amount. The transmission will stop once the selected amount and the counter match the value selected. This input used for user to enter the password to allow data transmission between computers. The transmission will only occur if correct password is entered as it satisfies one enabler condition. Before any data transmission can occur, the user must enter a 3-digit password. The password is 6C2 as we mentioned in the circuit. P0 represent the least significant digit and P2 represent the most significant digit. This password is verified using 3 4-bit decoders. Into the next system implementation input push button. A dedicated TRX clock button in the controller serves as the main trigger for data transmission. It sends a clock pulse to the counter and operates the data transmission between selected computer in Lab A and Lab B. The transmission will only happen if this button is pushed while other condition of clock enabler has been fulfilled. So for the next part is clock generator. The clock generator plays a crucial role in synchronizing the system. The clock generator in Lab A are designed to visualize the data packets being transferred from computers. When the clock generator is enabled, The data packet transferred to the selected computer in Lab B becomes clearly visible. This is demonstrated through the continuous switching between 1 and 0, which causes the LED display for computer in Lab B to blink, providing an indication of the data transmission. We jump to multiplexer. 8 to 1 mux, or as known as multiplexer, combines 8 input lines into a single output, enabling efficient data selection and transmission. It connects to 6 computers in Lab A, allowing one to be selected for communication with a computer in Lab B. Data select inputs linked to source switches determine the source address for seamless and controlled transmission. For example, selecting COM A5 assign the source address 100, ensuring its data is sent to the chosen computer in Lab B. As for the next one is demultiplexer. In Lab B, a 1 to 8 demux, or as known as demultiplexer, distributes the transmitted single input to the correct output line based on control signals. For example, if COM A3 is selected, the demux ensure the data reach the assigned COM B2. Synchronizing control signal between the mux and demux ensure accurate transmission, minimize error, and allows scalability for integrating more devices without major reconfiguration. We continue to the next one, which is decoder. 3 4-bit decoder are used for the 3-digit password. Each bit of the input hex digit has been connected to the input of the decoder, which will determine the truth value of the password entered. All output of the decoder are connected to an AND gate as the input, which will only give high output when all 3-digit password entered are correct. So for the comparator, a 4-bit comparator is used to compare the counter value with the amount of packet data selected for transmission. The result of the comparator is then connected to the clock enabler by a NOT gate in which data transmission will stop when both values are equal. So, for the 4-bit synchronous count-up counter, we use a 4JK flip-flop configured to function as a 4-bit counter. The inputs of all flip-flops are connected so that they operate as T flip-flops and count up. It's synchronous because the flip-flops are connected to the same clock source. The pre-inputs of all flip-flops are permanently set to 1, while the clear input are user control. These two inputs must be set to 1 for the counter to function synchronously. The clear input can also serve as a reset switch, allowing the user to reset the counter when needed. For the 7-segment display, the outhex output displays serve as an indicator of the current value of the counter, dynamically updating each time a data transmission occurs. The 7-segment display is configured such that its inputs are directly connected to the output of the flip-flops. This arrangement ensures that the displayed value accurately reflects the real-time state of the counter during operation. Let's see the next one, which is clock enabler. The clock enabler will function if 5 conditions are met. For the first one, the selected computer from Lab A and Lab B has been powered on. Next, the password entered is correct, which is 6C2. Then, clear bar switch in T flip-flop come up is set to 1. Next, current value of the counter is not equal to the amount of packet data selected. And lastly, TRX clock button in controller is pushed. The clock enabler ensures system reliability by synchronizing operation and maintaining functionality. If the conditions are satisfied, the clock remains disabled, thus preventing error and ensuring data integrity. Next, we jump to data sync. The mux in Lab A select a computer for data transmission and connect to the demugs in lab B via the sync data function. The mux output and clock enabler output pass through an AND gate which controls data flow to the demugs, ensuring transmission only when the clock is enabled. This setup enhances and acts as a control mechanism preventing unintended transmission and enforcing strict data integrity. Lastly, for the system implementation is LED display. The LED of the selected computer in lab B will light up during data transmission, indicating a successful transfer. If the selected computer's LED does not light up or another computer's LED lights up, it means the data transmission has an error. This issue may occur if the clock enabler conditions are not fully met.
Alright, now I will do the demonstration on how our design circuit works. Okay, first of all, the component design uses basic gates, which are AND gates, OR gates, and also NOT gates. We also use T flip-flops, multiplexer, demultiplexer, comparator, and decoder. So we have provide the user manual here for the user to refer whenever they use this circuit. So first step is to power on selected computers in lab A and lab B for data transmission. Alright, so before I start, we have to start the animation first. And then, okay, let's say we want to select computer A3 and computer B1, A3 and B1. So here we have to enable clock animation. Alright, the first step is time. Second step is to set source and destination addresses according to the selected computers using the switches. Okay, so this is the switches for the source addresses and this is the destination addresses. So these switches has been connected to the data select inputs for this multiplexer and for this demultiplexer. Alright, so as we have selected computer A3 here, so the source address should be starting for 0, 1, 2. So 0, 1, 2 is 0, 1, 0. And then for the computer in lab B is B1, so the destination address should be 0, 0, 0, 0. Alright, the next step is to enter the correct password. Okay, so this is the password. We have to enter the correct password here. So the password is 6C2. So this LED, the result LED will light up, means that this the password that we enter is correct. So let's say if the password entered is wrong, like 66C0, so the LED will not light up, means the password entered is wrong. So the decoder is the one which determine whether the password entered is correct or not. Alright, moving on to the next step. Number 4 is to set clear bar switch in TFF count up to 1. So in the counter we have the clear bar switch which we have to set to 1 for the flip-flop to change to the synchronous mode. For the preset clear bar preset bar input, we have permanently set to 1 so that the user only need to control the clear bar button. So the input of the JK flip-flops has been connected as what T flip-flop works. So even though we use the JK flip-flop positive edge trigger, but this JK flip-flop works as T flip-flops. Alright. So the next steps is set the maximum number of packet data to be transmitted. Okay, so we have to select this packet data. Let's say we want to select the maximum amount of packet data should be 5. So we know that when the counter value here and this value is the same, the data transmission will not happen. Okay, and then the next step is press and hold TRX clock button a controller to transmit one byte of data. So we have this controller, which will be the clock generator, or it will give a clock pulse to the flip-flops for the counter to work. So let's say if all the if all the conditions of the clock enabler have fulfilled, so this LED display will blink at the selected computer, which is B1. So this B1 LED display will blinking means that the data transmission from the computer A3 in lab A to the computer B1 in lab B successful. If I press and hold this button, the LED display will blink it, and the counter value also will change to 1. So let's take a look. Alright, so as I press and hold this button, the LED is blinking, and also the counter value is changing to 1. As I stop holding this button, so the LED will stop blinking, and I continue the data transmission. So the counter changed to 2, continue to 3, 4, and as we know, if we make another data transmission, or if we push this button again, this counter value will be 5. So 5 is same as the packet data amount that you have selected. So 5 and 5 will be equal. So the data transmission will not equal, means that this LED will not blink. So let's take a look. When I press this button, alright, so the counter changed to 5, but the LED is not blinking. Whenever I press this button again and again and again, the transmission will not happen because you have selected the packet data amount set to be 5 as the maximum. The last step is to reset clear bus switch for new data transmission if needed. So if the user want to reset the transmission, just reset this clear bus switch to 0 and 1 so they can start the new data transmission again. So that's all for the demonstration.
Now, the last part, conclusion and reflection. This project features a simple and user-friendly design incorporating essential components such as 4-bit decoders, input switches, 7-segment displays, LEDs, a 4-bit comparator, an up counter, and a max-demarc pair. A key enhancement was the integration of a password-based security system, ensuring that other components remain inactive if the password is incorrect, adding reliability and safety. The system successfully met its objectives, effectively managing multiple processes while maintaining ease of use and organization. Throughout the project, our strengths lay in troubleshooting and problem solving, allowing us to efficiently resolve design issues. The password security system was a major accomplishment, enhancing the circuit's practicality. However, incorporating additional features such as password setup, proof challenging, highlighting areas for improvement, and streamlining the design. Moving forward, we aim to develop more complex circuit with innovative features, applying the knowledge and experience gained to real-world applications and more advanced designs. That's all from us. Thank you for listening.